All right, so let's start. Last class we were discussing about the specific capacity and heat capacity, right? So I told you specific heat capacity. If you are doing experiment, you need to take either 1 gram or 1 kilogram, right? So you have an oven here. You have an oven here, and you put a cup here, and in this cup you are putting 1 gram water. 1 gram water, and you put a thermometer here. So thermometer at the beginning showing, let's say, 22 degrees centigrade. So you keep heating until it becomes 23 degrees centigrade, right? Just by 1 degree centigrade or 1 degree Kelvin, same thing. Yeah. So how much heat flows from this oven to this water on increasing the temperature from 22 to 23 degrees centigrade when the water is 1 gram, that much amount of heat is called specific heat capacity of that water. Make sense? Or you could do another way. So you can take a oven and put a big beaker here, put 1 kilogram of water here, 1 kilogram of water here, put a thermometer. So thermometer is 20 degrees centigrade here. So keep heating until it becomes 21 degrees centigrade. Just increase by 1 degree centigrade. And how much heat that flows from heater to that water, that amount of heat is called specific heat capacity. Yeah. So what is the heat capacity then? So that's a specific heat capacity. But for heat capacity, you can take any amount of water. So we can take 5 kilogram of water here, 10 kilogram, 20 kilogram, doesn't matter. Yeah. So keep whatever you like and put that in oven and put thermometer. Let's say it is now at 23 degrees centigrade. And now keep heating until the temperature becomes 24 degrees centigrade. Increase by 1 degree centigrade, right? So how much heat flows from this heater to this water to convert from 23 degrees centigrade to 24 degrees centigrade? That amount of heat is called heat capacity of this 5 kg water. Make sense? So if you take a small amount of water, it takes a small amount of heat. If you take big amount of water, it takes big amount of heat. Yeah. So heat capacity depends on amount of substance. So amount. So if you take small mass, it takes a small amount of heat. If you take big amount of mass, it takes big amount of heat. Make sense? Which is known thing, right? So if you go to the kitchen, you just want to make 1 cup of tea, so it immediately boils, right? But if you want to make tea for 10 people, so you need to put 10 cup of water. It takes a long time to, right? So same thing. Make sense? So amount of mass, amount or the mass. So it depends on, so the heat capacity depends on the mass. If the mass is more, you need to supply more heat here. Yeah. If the mass of this thing is small, you need to apply small amount of heat, right? And another thing is, so if you want to increase the temperature by a large number here, you need to heat more time. Yeah. But we just talking about the heat capacity. So let's talk about, we just want to increase the temperature of water by 1 degree centigrade, right? So another one is, so that's a quantity, and the size of the temperature change and identity of the material. So I really don't want to talk about this one. So our book are writing there, but it's irrelevant because we are just talking about the 1 degree centigrade temperature increase, right? Make sense? So if we have a large number of temperature increase, so we need to heat long time and it absorbs the large amount, right? So another one is, so let's talk this one, identity of material, identity of material, identity of material. So if you put 5 kg water here, it takes long time to heat that water. So it takes large amount of heat to change the temperature. But if you put iron or copper here, let's say 5 kg, it immediately gets heated. Yeah. So which material you are heating, it depends on that one. Yeah. So if you want to heat the water in kitchen, it takes long time to heat that water. Yeah. But if you want to heat a small piece of iron, it immediately gets hot. Yeah. So something gets immediately hot, something gets hot really. It takes really long time to get hot. Yeah. So water is the substance that takes the longest time to get hot. Yeah. It's very hard to heat water. So we'll talk in next slide. these are the material. People have done a lot of experiments. So they take 1 gram or 1 kilogram of substance and increase the temperature by 1 degree centigrade and calculated the specific heat capacity or the amount of heat required.
Oh my God.
1 degree centigrade. Yeah.
Really?
Oh, somebody here is talking. So, can you mute your please, Aman? Atman. All right. So, good. So let's start here. So this is here is a substance, and this is a specific heat capacity. So, if you take 1 gram of aluminum, so there is aluminum. So this gram means you take 1 gram of aluminum and you started to heat that and increase the temperature by 1 degree centigrade. So how much it absorbs? 0.897 joule. Make sense? So you took 1 gram of aluminum and you change the temperature of that aluminum by 1 Kelvin or 1 degree centigrade, same thing, and that will take 0.897 joule of heat energy. Make sense? Now let's talk a little bit down here. Let's go to iron. So it's iron immediately gets it. So it's not as hard as to as aluminum. So look here, aluminum. So if you supply 0.4 joule heat energy to 1 gram of iron, to increase the temperature by, it will increase the temperature by 1 Kelvin there. Now let's go and look here, water. Look here, water. So water, if you take 1 gram water and you started to heat it, to change the temperature by 1 degree centigrade, it really needs a large amount of heat, 4.184 joule. Yeah, so it's really hard to heat water. Make sense? So it's not easy to heat water. But if you want to heat oil, you put a little bit oil in the pan, it gets hot immediately. But if you put the same amount of water in the pan and heat it, it takes long time to make the water hot. Yeah. So water has a large specific heat capacity. So very hard to heat water there. So these are the number. If you take 1 gram of the material and you do the experiment. But how about here? Joule per mole per Kelvin. Here, so let's talk about the water. So if you take water, which is water? This water liquid here. So for liquid water, we have 75.4. So what does that mean? So joule per mole per Kelvin, right? So it's writing joule per mole per Kelvin. So in this case, you need to take 1 mole of water. So 1 mole of water is H2O. So look at the periodic table. H2O is 18, right? So H is 1, 2H2, oxygen is 16, so 18 grams. So if you take 18 grams of water in a beaker here and put in the oven, and let's say the temperature you want to change from 22 degrees centigrade to 23 degrees centigrade, you need to supply how much heat? So 75.4 joule of heat energy you need to supply. Make sense? The joule per mole per Kelvin is we will take 1 mole of water and do the experiment. And for joule per gram per degree per Kelvin, so we will take 1 gram of water and do the experiment. Have you got that? So it makes sense because if you take 1 gram water, it is saying, if you take 1 gram water, it is saying I need 4.18 joule, right? 4.18 joule, 18 joule. 1.18 joule. But if I take 1 mole is 18 gram. So if I take 18 gram, 18 multiplied by 4 with 4.18 would be approximately 75 joule, right? The same thing. It's just how we are expressing the value in different units. Make sense? So like that. So if something is we are doing the heating experiment, if something that immediately gets heated, it has a very small specific heat capacity. But if something is heated very slow, it has high specific heat capacity. So if you go to the beach, there is a water and there is a sand, right? And the sand is very hot. Put your foot in the sand, it's very hot. But put your foot in the water, water is cold, right? So water has a large specific heat capacity, so water doesn't get heated that easily. but sand has a very small specific heat capacity, so it is very hot when you put the foot in sand. Yeah. So same thing. So if you go to the outside and there is a black top, and somewhere there is a black top, and somewhere there is a no black top. So put your feet in the black top. It's very hot. Put your foot toward the soil. Soil is not hot. Why? Because soil has a large specific heat capacity, so it doesn't get heat easily. It doesn't get hot easily. But those black top, they have very small specific capacity. So a little bit sun comes there and fall there, and they become hot immediately. Make sense? So something that becomes hot very fast has a very small specific capacity. Yeah. So look here. So which are the lowest specific capacity? So 0.8, 0.1. So the gold has a very small specific capacity, 0.1. So if you want to do the experiment with gold, put the gold in the fire, immediately it becomes very, very hot. Make sense? Because gold has a very small specific capacity. So, and water, so which is the highest one here? So highest is the water. So put a little bit water and keep start heating. It never gets hot, right? So we keep heating like that. Yeah. So that's what it is saying. So this is the equation. This is a very famous equation, and we in all thermodynamics, no matter where you go and you study what kind of thermodynamics, we always use equation. So this is a very important equation here. So let's say I have let's say here 0.5 kg water, 0.5 kg, or I would say 500 gram water. I put 500 gram water in this oven, and I put this is on the oven here, right? So the beaker, I put 500 gram of water, and I put the thermometer here, and I still is not turning the heater yet. So let's say the temperature here is 22 degrees centigrade here, 22 degrees centigrade. Now I turn the heater and it starts to get hot and it boils, the water boils and the temperature is 200 degrees centigrade, right? Make sense? So I take a beaker, I put 500 gram of water and I put a thermometer there, and thermometer shows initially 22 degrees centigrade, and I put that in the oven and it starts to heat and it boils, and when it boils it reaches the 100 degrees centigrade there, right? So how much heat this water absorbs from heater to water? So that, sorry, how much heat go from this heater to water if this is the condition? So that is calculated like this. So heat absorbed by water, so that is Q. So we give the amount of heat absorbed by that water from heater. So it is going from here to here to boil the water, right? So that is given by this equation, MC T2 minus T1. So this is the equation. So M is the mass. So what is the mass? Mass is the 500 gram. 500 gram. And C is the specific heat capacity. What is the specific heat capacity of water in terms of per gram? So from previous page, we write the 4.18, right? So 4.18. So that C is 4.18. So grams. So in terms of grams, so let's go back here. So look here, water. The specific heat capacity of water, I'm going to use this number 4.184. So let's use 4.1. So 4.1. So that's a 4.1. This is 4.1. So this is gram, or this is also in terms of gram. So T2. So the temperature becomes 100 degrees centigrade from 22 degrees centigrade. So that's 100 minus 22. So like that. So you multiply that, whatever number comes there, that joule, that much joule, it is absorbed by that water to change the temperature from 22 degrees centigrade to 100 degrees centigrade. Everybody got that? So this is the equation. All of this class is using this equation. Yeah. So if you understand this one, everything is same. So let's go here. So here, 50 gram of water. So let's do this this calculation here. So this is saying I have 50 gram of water. So we put 50 gram of water in this oven, and then is warm from 25.3 degrees centigrade to 33.7. So initial temperature. So before heating, it was 25.3. 25.3 degrees centigrade here. And then after heating, that becomes 33.7 degrees centigrade. So that's a 5 gram water. So the equation is same here. So that's a 5, mass is 5 gram. C is always the same thing, 4.1, or you can write to 4.181, whatever, yeah. 4.18 and 4.1 would be almost the same answer. And T2 minus T1. So T2 I have 33.7 minus T1 I have 25.3, and just put this number in calculator. Whatever number comes here, that much joule of heat energy it gets. Yeah. So this is the fundamental equation in anything in everyday life. Yeah. So the electric bill or whatever bill comes into a house, all they calculate like this way. Make sense? Good. So they have a mass, they have a temperature difference, and the specific capacity. So specific capacity of water is 4.184 joule per gram, or you can just write 4.1. It's almost the same value. It doesn't matter. So did I get the plus number here or minus number here? So look here. So my final number is big number. Initial number is small number. So big number minus small number gives the plus value here. So this is the plus value. Plus value means heat goes from heater to water, not from water to heater, right? So it's impossible what the heat goes from cold water to hot heater, right? So always heat goes from hot things to cold. So water energy is increased. Why? Because water absorbs the energy, heat energy from heater. Yeah. So if you understand this concept, all is same thing here. So I'm going to show you other problem. So same thing here. So this is also same thing. So let's go here and so how much heat is needed to warm 250 gram of water from 22 degrees centigrade to 98 degrees centigrade. So this time they are asking us to calculate the amount of heat. So again, the equation is same here. So they put how much water there. So how much heat is needed to warm 250 gram. Now we have 250 gram water here, 250 gram water, and heating from 22 to 98. So they put the thermometer here, and at the beginning, before heating, it was 22 degrees centigrade. After heating, they have 98 degrees centigrade here. So how much heat it absorbs from going from here to here, right? When the temperature changes from 22 to 98. Make sense? Same thing. So Q is the amount of the heat going from heater to water. So that's M C T2 minus T1. Same thing. So M is I have 250 gram. C is 4.1. The specific capacity T2 is 98 and minus the T1 is 22. So just calculate whatever number comes here. So that many joule of the heat energy it gets out. Easy? Same thing. So there is no new thing. I am just going to use all the time the same equation here. So what is the specific? Let's do another one. In number 2, what is the specific heat capacity of the silicon? So this time they are asking us to find that C value. So this C value. So let's do here. So that number 2, right? So what is the specific heat of silicon? So that's a C value. They are not giving that specific heat capacity there. If it takes 192 joule heat energy, so Q is equals to MC T2 minus T1 is our formula. So heat energy absorbed is joule. So that much heat energy is absorbed on heating. So that's a Q, 192 joule. And then mass of how much mass of silicon. Silicon is 445 gram of silicon, and they are not giving this specific capacity of that silicon. And T2. So what is the temperature difference? So to raise the temperature of silicon by 6 degrees centigrade, meaning that if it was 30 degrees centigrade at the beginning, after the experiment is done, 36 degrees centigrade. So T2 minus T1 is 6 degrees centigrade. So that's a 6 degrees centigrade. Make sense? So they are not giving initial temperature and final temperature. They say, oh, I started heating at certain temperature and then make the temperature increase by 6 degrees centigrade, right? And what is the specific heat capacity? So basically, what they were doing is, so they have a beaker here. So they put 45 gram of silicon here, 45 gram of silicon, 45 gram of silicon, and they started to heat it. They put the thermometer here. So if it was at 15 degrees centigrade, they heat until it reaches to 21 degrees centigrade by 6 degrees centigrade increase. Make sense? You got that? So like that, and then we don't know the specific heat capacity of this one, so we need to calculate this C. So 192, I'm going to put this 45 and 6 down here, 45 and 6 down here, that is equals to C. Whatever number comes, that is the specific heat capacity value in terms of joule per gram per degree centigrade, right? Because my thing here is joule, degree centigrade and gram. So whatever number comes there, joule per gram per degree centigrade. Easy, right? So whatever is not given, we just calculate. So, not given. So yeah. So again, so we are doing the same thing here, but this is a little bit difficult. But other the equation solving and equation is same. So let's do this one. So here what they are asking is, I have 145 gram sample of copper metal at 100 degrees centigrade, and that is placed in 250 gram of water at 25 degrees centigrade. So this look here. So we have a water here. So this is the water. This is the water. So water. How much water I have here? So the water. 250 gram of water at 25 degrees centigrade. So this is thermometer, it says 25 degrees centigrade here. So water. So mass of water I have is, let's say I write the mass of water is M1, and that is equals to 250 gram. 250 gram, right? And water at 25 degrees centigrade. So the temperature of this guy now is 25 degrees centigrade. Let's write that is at 25 degrees centigrade here. And then so I need three things. So Q is equals to MC T2 minus T1. So I have the mass of water, I have the temperature of water T1, but I don't have, they don't give the specific capacity here. So I put that C1 is 4.1 whatever joule per gram per degree centigrade. So C1 is always safe for the material, yeah? So for water, it's always 4.1, yeah? So that's water. Now what they did is they put 145 gram of copper at 100 degrees centigrade. So there was a copper here, copper. So this is copper. So there are some copper pieces, and the mass of copper M2 was 145 gram. 145 gram. And the temperature of this copper is, let's say T1, that is equals to 100 degrees centigrade. So that's 100 degree centigrade, like this. So M2, so for this one, I have that, you can write that M1, M also, it really doesn't matter there. So let's do that. Now what they do is, so this is very, very hot, right? And then they throw all these things into here. Make sense? So they have a very, very hot copper and they have a cold water. Now the hot copper, they are going to dump into the water, right? And what happens when they dump this to this water? So they dump that here. So I have water and I have, they dump all copper from there to here. Here, and they put the thermometer already there. So they have water and copper mixer. So they dump this one and this there. And in Kelvin, when the system reaches thermal equilibrium, the temperature of the water and the calorimeter is 28.8 degrees centigrade. So now they have 28.8 degrees centigrade. 28.8 degrees centigrade. Yeah. So what happened here? So copper was very, very hot. It lost the heat to the water, right? And the water was cold, so its temperature now started to increase, right? Make sense? So the copper lost the heat to water, and water gained the heat from the copper. So what happened here? So let's do that. So they're asking us to calculate what is the specific heat capacity of copper, and what is the amount of heat of for 100 gram piece of copper. What is the amount of heat for 100 gram of piece of copper? So we'll discuss that later. Let's look here. So what happened here is there are two guys. So one is Q1, another is Q2. So what happened here is copper give the heat to water and water receive the heat, right? Make sense? So I have very hot copper and a cold water. So I just throw the copper to water. So one guy is going to lose the heat, another guy is going to get the heat, right? So let's say I have 3 pens. I have 5 pens, so I want to give somebody 3 pens. So I lost 3 pens and you get 3 pens, right? So those numbers are equal, right? So whatever value one is losing, another is getting the same amount of value. So which one? 145. So let's look. This is a copper. So this copper guy is losing the heat. So we write the minus. But you really don't have to write the minus here. So this what is gaining the heat, we write for plus. But you really don't have to write plus or minus here. So if you want to write, why I write minus here? Because copper was too hot, so it gives the heat to the water, right? So that means water lost the heat. So if I have money, I give somebody my money, so I am minus, right? And somebody got my money, so he's a plus, right? So that's just like the money here. So let's put this one here. So this is the copper. This is the copper side. Copper side. This is the water side. So let's put copper side. The copper side M1, M or C T2 minus T1. So this is for copper side, and this is for water side M C T2 minus T1. So equation is always the same. Yeah. So this is the heat used by copper. This is the heat get by copper. So how much water, how much heat copper lost, that much heat water gain, right? So both numbers are equal. Listen. So let's put the value there. So how much mass copper has? 145. 145. So did they give the value of C, the specific capacity of copper? No. What is the specific heat of copper? So we want to calculate that one. So I don't know specific capacity of copper. And what is the temperature change of the copper side? So at the beginning, copper was how much? 100 degrees centigrade, and the final temperature was 28.8. So so 28 20, so the T2. So T2 is the final after mixing, right? So after mixing, I have 28.8. So before mixing, the copper has 100 degrees centigrade. 100 degrees centigrade. Now is equals to M is the mass of water. So mass of water is how much mass of water? 250 there. So 250. So specific of water is 4.1 and T2. So before mixing, so T2 is after mixing, right? After mixing, I have 28.8, 28.8, and before mixing, I have water temperature is 25, so 25, like this. So all are number except this C. We need to calculate that C, right? So one side you are going to write about the copper, another side you are going to write about the water, and what is not given, you are going to solve the equation. Yeah. So now I have everything ready here. So let's do this. So I just want this C here. So that C is equals to all other things are number there. So 250 multiplied by 4.1, then 28 minus 28.8 minus 25. So and then you divide by all these number goes down. So this number and this number go down here. So that is 145 and 28.8 minus 100 degrees. So whatever number comes there, that is the specific capacity of copper. You got it? So after mixing, that is T2. That's the only thing we need to understand. Yeah. So when I mix the very hot thing with the cold water, then will be the temperature of water is going to increase a little bit. That is the T2 for both. Yeah. So like that, and you just calculate, put the number in calculator, and whatever number calculator is, that is the specific heat capacity of copper we get. So on doing that, you will get. So I don't know. I didn't calculate here. So while you are calculating the specific heat capacity and mass, if you get negative number, just disregard it. Mass cannot be negative. We cannot say a mass, my mass is minus 50 kilogram, right? So if some reason there comes a minus sign, just disregard that. And also specific heat capacity cannot be negative. So if that there comes the negative sign, just disregard that also. Yeah. Everybody got that? So because specific capacity and mass cannot be negative. So like that. So what is the amount of heat for 100 gram piece of copper? So if we have to calculate the amount of heat, so Q is equals to MC T2 minus T1. So you already got the value of C from here for copper, right? So just you are going to put that one here. So whatever the number comes from there, just put. So M is for that M is how much? 100 gram. So if you have 100 gram, so the copper specific capacity comes from here, right? Or you can just look the table also. So put that number here in T2 minus T1. So what is the temperature change here? So what is this amount of heat of the 100 gram piece of copper? So T2 was 28.8, T1 was 100 degrees, right? Make sense? So like that. So only the C value. Just put that C value there as M as M and T2 minus T1 are the same. Why I put 28.8? Because we are just talking about, I put the hot copper in the water and the temperature, the final temperature of that mixture was 28.8, right? And initially that the copper was 100 degrees. Make sense? So like that. Yeah, but I really don't like when people just put all multiple questions in the single, multiple problem in the single question here. So let's go another one here. The same thing here. So let's do this problem. So again, we just mix two things and look the temperature and what they want us to calculate. So what are they saying here is mixing two things with different temperatures. So a 55 gram piece of metal is heated to 99.8 degrees centigrade and then put to the beaker of water, right? So same thing. So you have a 55 gram piece of metal. So some metal is here. So that metal has 55 gram. So mass is 50. This is metal. So metal, I have 55 gram. So that's that much there. And heated to 99.8 degrees centigrade. So the temperature of this one is 99.8 degrees centigrade. So already heated. And plunged into the beaker of water, the beaker holding 225 gram of water. So there is another beaker, so that has 225 gram of water, 225 gram water. So this is water side. The water, that's a mass, and its temperature is 21 degrees centigrade. So the temperature, they have thermometer here, so this is showing 21 degrees centigrade. They have thermometer here, that is showing 99.8 degrees centigrade here. Like that. So now they are going to throw this one to this one. So when they throw those metal to here, so what happens is something like this. So they have that metal here and they have water here. So and then how much temperature they have here? So 21. Now before the metal contact, the final equilibrium temperature of the system is 23.1. So when we mix both things, so the temperature becomes 23.1 degree centigrade. So this is the T2 for both. Yeah, makes sense? After mixing, whatever the temperature comes there, that is the final temperature after mixing. Makes sense? So now write the equation. So this is the metal side. let's write this one. So that's a Q. This is a metal side. This is the water side. So Q is equals to Q, right? One is being giving out the heat, another is taking out the heat, and both heat amount are equal. Why? Because one is giving to the another the same amount of heat we can take, right? So if I give a 3 pen to you, you get 3 pen, I lost 3 pen, like that. Yeah. So Q is same thing. So M C T2 minus T1. So this way also M C T2 minus T1. So these are for water, these are for the metal, right? So or you can write the M1 C1, whatever like this. M2 C2, you can also write that way. It doesn't matter. Yeah. So what is the mass of the metal here? 55. What is the specific heat capacity of the metal? They are giving. We need to calculate what is the specific heat capacity of the metal. So they are not giving this value here. So see, so T2 is the mixture. So that's the temperature of the mixture, 23.1 minus the T1. So T1 is this one, 99.8 is equals to M2. This is the water side. Water has 225 and water's the specific heat capacity of water is 4.1 and T2 minus T1. So this is T1, this is T2. So 23.1 minus 21, like this. Everybody got that? So the T2 is after mixing two things, one is the temperature, that is T2. So that is the one thing we need to take care here. So now other thing is everything is same. Now we need to calculate this value. So you need to calculate this C value. So you can do calculation here, or you can do later after taking this side. So 225 multiplied by 4.1, 23.1 minus 21, and all this number come here. So 55 and 23.1 minus 99.8, and just put those number in calculator, calculate the answer. And I told you, if some reason you get a negative number in calculation, just get rid of that negative number, because specific capacity cannot be negative, mass cannot be negative. When we are calculating the mass and specific capacity, if negative number comes there, just get rid of that. Yeah, and I will tell about how to do the temperature later. So like that. So do the exercise, and so all things same. So calculate the specific capacity of the unknown metal if it requires a Q is very simple here. Joule energy to raise the temperature of 21.1 grams of this metal by 34.6 degrees centigrade. So this is T2 minus T1. Yeah, there is no T1, there is no T2. So we need to increase the temperature of metal by 34.6 degrees centigrade. Means that's a T2 minus T1. So Q is equals to mCT2 minus T1. So Q is given. So calculate specific capacity. So we need to calculate C of an unknown metal if it requires 195 joules of heat energy. So this is 195, and M is given how much? 12.1 gram. So this has 12.1 gram mass, and then C is not giving, and T2 minus T1 is 34.6. Yeah, so by 36 point. So this is giving that, not giving T1 and T2, but he is already subtracting T1 from T2 and giving that number. Make sense? Easy. So just calculate that, whatever the number C comes. So this number 195 divided by 12.1 multiplied by 34.6 is equal to C. So it is 195. So I put this number down, and that's C. Good. Simple. The same thing here. When a piece of copper 5 grams, so this is mass, it takes 2 seconds. So time has nothing to do here. Yeah. So 2 second time, don't worry about time here. And 100 joule of heat energy. So this is Q. 100 joule means that's value of Q. And the copper, the temperature increased from 20 to 71.9. So T2 minus T1 is 71.9 minus 20, whatever comes there, that's T2 minus. Yeah. So put all value there. And specific capacity of the copper. So whatever after calculation comes, that's 0.85. So let's do some problem here. So that mixing problem, most likely that mixing problem will be in exam, yeah. So I just put 100 degrees centigrade copper and throw into water, and this is the final temperature. So something like that, yeah. So just practice that mixing this problem. Mixing, or maybe there is a coffee cup calorimeter. So the coffee cup calorimeter we will be doing in the laboratory. So maybe that one. So we'll see which one. So let's look this one. So a series of equal mass sample of 5 materials listed in the table are brought from room temperature to 100 degrees centigrade. Which sample require the least amount of energy, meaning that which substance will get very hot very fast, right? So which has a small value of the specific heat capacity that becomes hot very fast. Yeah. So look here. So let's look here. So aluminum has 0.9 specific capacity, pyrex 0.75, iron 0.4, lead 0.1, water 4.1. So which becomes very hot very fast. So that's the lead, because lead has a small amount of specific capacity, right? Which will be take a long time to be hot. So that's water, because it has a largest amount of the specific capacity. Yeah. So I think in the universe, the only water has that high specific capacity. It really takes large amount of heat to make water hot. Yeah. So here also the same thing. So when a piece of copper at a temperature of 256 degrees centigrade is added to the 255 grams of water at temperature T1, the final temperature of the resulting mixture is 24. If the specific capacity is given, what is the mass of the piece of copper? So again, you just calculate the mass. Previously, I was calculating the specific capacity. Now we are calculating the value of M, right? Exactly same. And I told you, if some reason negative number comes with the mass, that's the, we just disregard the negative number. Yeah, the same thing. So same thing here. So calculating temperature. So we need to be careful here. So I will talk a little bit here. So previously, when I was calculating the mass and specific capacity, I told you just if you get a negative number, just get rid of that one and write the answer, right? So here, in case of temperature, we cannot do that, because if we disregard the sign, rather than coming too high, sometimes it goes too low. So we need to take care of the negative sign here. So let's do that one. So since we are calculating the temperature here, so I think everything is same here. So 15.238 gram piece of zinc metal is placed in a sunny window. The initial temperature of the piece of zinc is 29.5 degrees centigrade. It absorbs 495 joule of heat. What is the final temperature of the zinc piece, right? So this is saying what is the final temperature of the zinc piece. The specific capacity of this one is this one. So let's do that one. So you have a small piece of zinc and you put in the window, and the heat comes from the sun and it becomes hot, right? So Q is equals to MC T2 minus T1. So always this is our formula. There is no other formula here. Yeah, Q is equal to MC T2 minus T1. Now is it's become hot or it's becoming cold? So the initial temperature of this is this one. It absorbs 495 joule of heat. So there was a zinc, and heat comes from the sun, and the zinc starts to absorb the heat, right? It takes the heat. So it takes the heat means this is the plus sign. Make sense? Because the zinc becomes hot, it is absorbing heat. So if we absorb something, we become plus. Yeah. So we need to write, when we calculate the temperature, we need to take care that plus or minus here. So if the zinc was throwing out the heat, that will be minus here. Yeah. So all other thing is same. So how much heat it absorbs? It absorbs 495 joule of heat energy. So that's a plus 495. Now, what is the mass of the zinc? That's a 15.2. So I just write 15.2. I really don't need that many significant figure there. And what is the specific capacity of zinc here? That's 0.388, 0.388, 0.388. And what is the final temperature? I don't know. So how much final temperature of that zinc is when this absorbs that much joule of heat from sun, right? And T2 minus the T1. I have the T1. So initial temperature of the zinc is 29.5. 29.5. So I think you can easily do the calculation. So you can multiply this one and put that value down there. So just put like that way. So that is 495 plus multiply by divide by, so this number and this number goes that way, right? Divide by 15.2 multiply 0.388 and is equals to T2 minus 29.5, like that. Now you do the this number in calculator and that gives me 83.7. So this 83.7, this is plus value. And then that's a T2 minus 29.5. So this guy will this way. So plus 83.7 plus 29.5 is equals to T2. So this plus goes this way, this minus goes this way, and that becomes plus there. So how much number that comes there? So 113.2 degrees centigrade. Got it? So when we are, so this is it's pretty simple, but later on, if something is losing the heat, we should be putting minus here. Yeah. If we don't put minus or plus while we doing the temperature calculation, we will easily make mistake. Yeah. So if something gets hit, the heat value should be written as positive. If that is losing the heat, that heat value should be written as negative, while we are doing the temperature calculation. But when you are doing the mass calculation or specific calculation, although minus sign comes there, you can easily say, oh, this is mass cannot be negative, specific capacity cannot be negative. So you can just write whatever you like. Yeah. But while doing temperature, I think I would not make mistake because I did this kind of problem long time, so I know easily what is going on, right? So, but you can get easily confused. So the best way is if something is losing heat, write minus here. If something is gaining heat, write plus it here, and that way you never make mistake. Good. But if someone, so I read the book. So some people just do all the time they put plus here, and when they give the conclusion later, oh my. Since it was getting hit, so I am going to add something like that, and they do that kind of things. But when we start practice in beginning, we must write minus or plus here. If something is losing, write minus. If something is gaining, write plus. And while we calculate temperature, never become mistake. Everybody got that? Good. So, all right. So we'll continue. You too.